Welcome. Today we are learning to simplify radicals some more. The first challenge that we have is simplifying radicals that have variables in them. It is not much different from what you've already learned how to do. Take a look at this. Remember that the first thing I'm looking for are perfect squares. So watch what I can do. Here's my radical. I'm going to split this. I'm going to factor it. But I'm not going to factor it all the way down to primes. I'm going to leave it as 2 times 100. Why? Because 100 is a perfect square. How about w to the 4th power? Look what I can do with that one. There we go. X can't be factored. There's only one of those. Now let's see. Let me remind you of the steps real quick. Take a look over here. First we factor and write all the factors under the radical. We're going to circle the perfect squares. Where are the perfect squares that you see? Well, we know that 100 is 10 times 10. So we could write this as 10 squared, right? 10 times 10? Now, let me see if I can find a good color here. A bright red. I'm going to take all the perfect squares that I see out. Here's 1. Good. Here's 2. Here's 3. Okay. Just to be clear, we're not really taking the perfect square out from under the radical. What we're really doing is taking the square root of the perfect square out from under the radical. So we end up with 10 from here times w times w. So that's going to be w squared. Now what's left inside? Let's go back to the pink. What's left inside is just 2 and x. We took the perfect squares and took their square root out. The imperfect squares we can't change. Okay. I have a question for you. Did we have to do this blue step? Did we have to change 100 into 10 squared? Not really. If you know that 100 is a perfect square, you could just circle the 100 and take the square root of 100 out. Let's move on. A couple more examples. Watch this one. Or try it yourself. Pause the video and then watch. There's my radical sign. I'm going to factor 45. 4 times, no, I did that wrong. Silly me. It's 5 times 9. I know that 9 is a perfect square. I've also got p cubed. Watch what I can do with that. I can split that. That's the same thing as p times p times p. I could write it out as p times p times p over here, or I could write it out as p squared times p. Doesn't really matter. Now, let me get my blue. I know that this one is 3 times 3. Let me find my perfect squares. Here's 1. Take that out. Square root of 3 times 3 is 3. Here's the other one. The square root of p times p is p. So you end up with 3p on the outside. And on the inside, we're left with 5p. Okay. One more example for you here. Let's see. Let's go back to pink. Let me give a little bit more space because we might need it. All right, first step, let's make a big radical sign. We're going to write all our factors underneath. Okay, 32, I'm looking for perfect squares. Is there a perfect square that's a factor of 32? Well, sure, 4 is. 32 is 4 times 8. Now 8, can I leave 8 like that? It's not prime and it's not a perfect square. That means I need to keep factoring. Can I think of a perfect square that's a factor of 8? Of course. 8 is just 4 times 2. Now we've got perfect square, prime. That's good enough. R squared, that's already a perfect square. R times R. S to the 4th. Is that a perfect square or not? It is a perfect square. We can say that that's S squared times S squared. Finally, we've got t to the 5th. How do we do that? Well, we can say that's the same thing as t squared times t squared times t. All right, let's find our perfect squares and move them out from under the radical. We're going to move the square root of the perfect squares out from under the radical. Look at this, I've got a pair. What's the square root of 16? 4. Square root of r squared, that's going to be r. Here's a pair. I could do this one two ways. I could take square root of s squared is s, square root of s squared is s, or I could just say the square root of s to the 4th is s squared. Just saves a step. I'm all for saving steps. Oops, I forgot to round my arrow. So what do we have? We've got 4 times r times s squared times t squared times the square root of what's left inside? I've got a 2 and a t left inside. 2t. All right, what do we do if there are numerators and denominators? Well, that's actually pretty easy. We can split this radical into 2 radicals, one for the numerator and one for the denominator, like this. So that makes it a lot easier. 25 is already a perfect square, and 144 is already a perfect square. I don't even have to factor those. I can take out the square root of 144. I can take out the square root of 25. I end up with 5 over 12. Is there anything left inside the denominators? I mean, inside the radicals? No. Let's try this one. Here we go. What would I do with y to the 8th? I can split that into a pair. Y to the 4th times y to the 4th. This one, that's already a perfect square, 6 times 6. I could write 6 times 6, or I could just write 36. Watch this. Perfect square. We take the square root of 36, it becomes 6. We write this one as a pair to help us see. The square root of y to the 8th is y to the 4th. So we've got y to the 4th over 6. Anything left under the denominator? No. Okay, notice this pattern. Square root of 3 times square root of 3 is the same thing as square root of 9, which is just 3. Square root of 7 times the square root of 7 is the same thing as the square root of 49, which is just 7. Square root of y times the square root of y is the square root of y squared, which is just y. Square root of z squared times the square root of z squared is the same thing as the square root of z to the 4th, which is just z to the z squared. Know that pattern because it's going to help you right here. Okay? This is not simplified. Okay? There's a couple of reasons why it's not simplified. The main reason is because you cannot have a radical in the denominator. A couple of reasons why is that it's really hard to estimate what a fraction is when there's a radical in the denominator. And also it's really hard to add and subtract radical expressions when there's radicals in the denominator. So no radicals in the denominator. Okay? Question, why can't we just reduce this fraction? Why can't we say this is the same thing as 2 over root 3? The answer is that this is not a 6. I mean, this is not a 6. This is the square root of 6. The square root of 6 is an irrational number, 2 point something. Okay? 2 is not a factor of the square root of 6. So you can't do that. So let's try it this way. We want to be able to get that 6 out of the denominator. And what we're going to do is use this strategy, which is called rationalizing the denominator. We're going to multiply this fraction by 1. If we do that, are we going to change the value of the fraction? No, because when you multiply by 1, you don't change the value. But we're going to write 1 in a special way that's going to help us. We're going to write it as root 6 over root 6. Can you see that this is still equal to 1? Now what happens? Let's multiply numerator times numerator. You get 4 root 6. That's just 4 times root 6. When you multiply root 6 times root 6, what do you get? 6. Now can you reduce? Let's see. 4 is just 2 times 2, so we can take a 2 out of that. 6 is 2 times 3, so we take a 2 out of that. We end up with 2/3. So the answer is 2 root 6 over 3. Here are the steps. Let's do a practice here. All right, what happens if you have something like this? First step, let me give you a hint. It's going to look like this. Do that first. It's going to be 28 over 6. Now question, can I reduce 28 over 6? I can, because they're both under the radical. If they're both under the radical, then I can reduce. I can take a 2 out of each one. This becomes 14. This becomes 3. So I have the square root of 14 over 3. Next step, let's split the radical sign. Square root of 14 over square root of 3. Now we have to rationalize this denominator. Let's get a new color. I'm going to multiply it by 1, but I'm going to write 1 in a special way. How should I write it this time? I'm going to choose root 3 over root 3. See how that's going to work? Now I'm going to get what's 14 times 3? 4 times 3 is 12. 3 times 1 is 3. Carry the 1 makes 42. Square root of 42 over 3. Now I check. Can I reduce this? Are there any perfect squares in here that I could take out? The answer is no. This is just 3 times 2 times 7. No perfect squares. So this is your answer. Let's try this one. First step. Let's put it under one big radical and see if we can reduce first. So I've got 10xy